Okay, when you have a current flowing through a single current carrying conductor, like this one here, going in this direction, you have magnetic field lines produced around the wire. Okay, imagine like a big cylinders, a collection of them outside the wire. But we'll just draw a cross section of the cylinders and it looks like this. Okay, when you draw them, I mean, they should really get wider and wider because the strength decreases. Now what you do is you do the right hand grip rule, so you actually sort of grip the wire, imagine gripping it. Your right thumb goes in the direction of the current, so it's vertical, and your fingers wrap around the wire going around in this direction. Okay, so your thumb was pointing up, and then you wrap your fingers around the wire in that direction. Okay, not the best picture, sorry. Now let's say you were looking straight down at the wire. Okay, so in this case the current in the wire is going into the page, and that's the wire coming out of the page. So that very first circle is the wire. Okay, now so put a dot there in the middle so it's coming out. Now so if it's going into the page, your thumb points down and your fingers are going to wrap around the wire in a clockwise direction. If your current is coming out of the page, then your magnetic field lines are going to go in an anti-clockwise direction. Now the strength of the magnetic field depends on the size of the current, so if you increase the current, you'll make a stronger field, and it gets weaker as you go out. Okay, so magnetic field lines, remember, show two things: direction and strength. Now when we have a solenoid, okay, what we're going to do is we're going to wrap some wire around this metal bar. Okay, we can attach it to a power supply like that, and we'll have a current now flowing around this way. Now each of these wires, if we cut them, you'll see them coming out like this, and so in this case it's going into the page at the top and out of the page at the bottom. Okay, now the magnetic field lines around each of these, you can use the right hand grip rule. So this one's sort of going around this way, and so is this one. At the top there, it's going around the other way, but in the middle, it's pointing in the same direction. So what happens is all the field lines actually line up and join together. Okay, so what that happens is it essentially goes through and looks like effectively a bar magnet, like that. And you can see that because all these in the center here, all these arrows are pointing to the left. That is the direction they're all going to join up, and they all point to the left. So that means north must be at this end and south is at that end. Okay, so what you could do is on this image at the top here, draw those, okay, and then on this one here, draw the actual field lines. Google it if you want to find a nice image. Remember to put in the current directions. So note that the field is concentrated inside the solenoid but is spread out through the space outside the solenoid. You look where the wires are closer together. The closer they are, the stronger it is. The direction can be reversed by direction of the current, and then also the strength can be changed by the current. And also you can add more windings as well, more coils. Okay, now you must use iron because it is not permanent. Okay, it means it can be demagnetized. So if you were lifting up cars, you can use the iron to demagnetize, so you can actually drop the car afterwards. So when the current is switched on, the iron is easily magnetized, and when the current is switched off, the iron easily loses its magnetism. The strength of electromagnet increases if the current is larger, the number of coils is larger, and the poles are closer together. Okay, so uses One is a relay. Okay, we talked about this in class, but effectively we have a electromagnet here, and when the current is going, it brings this arm in, which lifts up this arm here. Okay, and that would actually make the contacts there touch together. The electric bell is very similar. Okay, in this case, as the button here is pushed, a current will flow and it will attract the hammer in towards the magnet, and as that happens, the contact there will actually disconnect, current will stop, and that means the hammer will then flow back the other way. Okay, now let's say we had a current carrying conductor in a magnetic field. So let's do a few different options. So one, we'll just draw some crosses. So some crosses are here, and that's showing the magnetic field B going into the page, and in this case here on the right, the magnetic field is coming out of the page. You imagine it just like an arrow. Okay, so you've got your feathers at the back of the arrow. You're seeing the feathers over here, and you're seeing the point come towards you here. Now, what we're going to do is put a current carrying conductor here inside this magnetic field and inside that one there. Now these are going to feel a force given by the left hand Fleming. So first step is, remember FBI, so your thumb is your F, your force, first finger is magnetic field, and your second finger is the direction of the current. Okay, so I. So first step, let's do your first finger, so your trigger finger, point it down into the page for the left hand side here, point it into the page, and then move your second finger, or your three fingers if they're together, pointing up the page, and you should be able to work out that there is a force to the left. Okay, and on this one over here, it's going to be on the right here, with the magnetic field coming out of the page, is going to be the opposite. It's going to be a force to the right. So right or left before? Can't remember. Anyway, so they'll be to the right. Now, if we actually have a beam of charged particles, which effectively is a current, then you'd also get some sort of deflection. So let's say we do a magnetic field again, and we now fire in an electron. Okay, so we've got a little particle, electron particle, is flying in. Now, the important thing here is you realize that conventional current always opposes the flow of the electrons. Okay, if this was a proton, it'll be in the same direction. If there's a flying proton or a flying helium nucleus, something like that, it would be a positive charge, so it would be in the same direction as the current. But in this case, the electron always opposes conventional current. So when you do this with your FBI, make sure you point the eye to the opposite direction the electrons are moving. So in this case, the electrons, the current will be pointing to the left, and magnetic field into the page, so the force is going to be down as it goes through the magnetic field. And when it does that, it actually goes and creates a circular path. Okay, now we've got a coil of wire that's A, B, C, D in between two magnets. Okay, so let's say that was north, that was south, like this. Okay, the magnetic field goes to the right in both cases. If we use left-hand Flemings on the wire between A and B and C and D, I'll talk about B, C and AD soon. If we look at those two, you'll find that if we had the current going around this way, then the force on this side here is down, and the force on that side there is up. Now B and C, if you try it, you'll notice that your first finger and second finger actually go in the same direction for the wire BC, and that means there'd actually be no force produced. Always have to be 90 degrees. Now, what happens is this coil is actually going to start to rotate. Okay, so eventually it's going to end up in a different place. Now what's happened here is our coil is rotated around, okay, so it's rotated around and is past the middle point. Now unfortunately the force, since the current hasn't changed on the wire CD, is still up is the force, and down on the one over this side. So what's going to happen is it's actually going to rotate past the center and then rotate back again, and it's just going to oscillate. So what you actually need to do for these, you need to put in a split ring commutator to make sure the current changes direction. Okay, so that coil's gone over halfway and it's now going to try and force it back the other way. So you can see here is the split ring commutator. As these two rings rotate round, then these brushes will then touch a different side of the coil on the next loop, next half. So current will flow in the direction ABCD, causing the coil to rotate anti-clockwise. After half a turn, the direction of the current is reversed, thus maintaining the anti-clockwise motion. Increasing the number of coils, increasing the current will increase the effect.